Hello, this is a lecture for section 3.6, complex zeros. Let's just take a minute. Let's start by taking a minute to review what we've talked about so far regarding the zeros of a function. We've been primarily focusing on the real zeros of a function. And recall that real zeros of a function occur where that function intersects the horizontal axis, right? So if I drew a little sketch here of a function, call that f of x, right? The real zeros of this function are going to occur here, here, and here, right? It's where the y coordinates are 0, or where the output of the function is 0, or we could also think about that as the horizontal intercepts, okay? So that only applies, however, to real zeros. Real zeros. Let me ask you, or let just take for a minute, think about this polynomial function here that I'm drawing now. Okay, we should all recognize that as a quadratic function, right? That might even be the toolkit function, just shifted up some number of units, right? But as we can see, call this guy g of x, there are no horizontal intercepts, right? There are no horizontal intercepts. Does that mean this function doesn't have any zeros? It does not. This function still has zeros, but the zeros of this function are not real. So we could say there are no real zeros. There's no real zeros, but we do still have zeros of the function. The zeros of this function will be complex zeros. All right, let's take a minute to review what a complex number is. A complex number is a number that consists of a real component and an imaginary component. Okay, real component and imaginary component. A complex number takes the form a plus bi. A and b would both be real numbers. I, of course, is the imaginary number, which is defined as the square root of -1, right? So, to simplify complex numbers, or to write them in their proper form, we need to, let me back up. All right, when we're dealing with complex numbers, usually a complex number is the result of taking the square root, the fourth root, or some even root of a negative radicand. Like this first example here, the square root of negative 25. The square root of 25, we all know that's 5, right? But what's the square root of -25, right? That's a little bit harder to think about. We know that the square root of 25 equals 5 because 5 squared equals 25. However, what squared would equal -25? Nothing, right? So what we need to do is we need to employ the imaginary number here, which we refer to as I, and recall that the definition of the imaginary number is the square root of -1. All right. So I could then rewrite the square root of -25 as the square root of -1 times 25. Right? It's the same as -25. And then I could break that up and write that as the square root of -1 times the square root of 25, right? And by definition, the square root of -1 is I. So I could make that substitution, and I could call this I times, and what's the square root of 25? Well, of course, that's 5. I times 5, written in its proper form, would be 5I. All right? This is probably the most basic complex number. The real part, what's the real part of this complex number? Remember, all complex numbers have the form a plus bi. Well, in this case, the a is just 0, right? I could write that as 0 plus 5i. It's still the same value. Right? Look at another example. What if I needed to simplify 4 plus the square root of -20? divided by 2, right? Well, I go through the same process. You might even think about a shortcut here. I can see this is always going to happen if I've got the square root or the fourth root or any even root of a negative radicand. I can go through this process. What I can do is I can sort of just the shortcut here would be to pop an I out front and drop the negative, right? So I could rewrite this as 4 plus I times the square root of 20, because of course the square root, or I is the square root of -1, right, over 2. And then I could further simplify this. Let's see, the square root of 20, well, that'll simplify to 4 plus, let's see, I times, square root of 20 is 4 times 5, and of course the square root of 4 is 2, right? So this could be 2 square roots of 5 over 2. Okay, and now I can simplify both of my terms in the numerator are evenly divisible by 2, right? So I could then rewrite this as 2 plus I square roots of 5. Okay, and we often stick the I out front, although technically, look at the standard form here. The square root of 5 should be in front of the I. So technically, this should be 2 plus the square root of 5 times I. But, you know, it's kind of a standard. It's okay to write it that way because that I sometimes gets accidentally tucked under the radical if we write it after. All right. So we can do arithmetic with complex numbers. To do arithmetic with complex numbers, I often think about this as doing arithmetic with binomials, right? That's how I like to think about it. I like to think about this I as if it was a variable. It's not. It's the imaginary number. But when we do arithmetic with it, we can treat it like it was a variable. So if I'm adding two complex numbers like this, all I'm really doing is combining like terms, right? That's all I'm really doing is combining like terms. So the real parts, the 2 and the -5, 2 plus a -5, well, that's 2 minus 5, right? Or -3. And then we have a -3i plus a -I, that's -3i minus I, or minus 4i. All right, subtracting complex numbers. Do you know what I like to do? I like to just distribute this negative, and then just combine like terms, right? So I can have 2 minus 3i, and then minus a -5 would be plus 5, and then minus a -I would be plus I, right? Then when I combine like terms, I've got a 2 plus 5. That, of course, is 7. I have a -3i plus I, that of course is -2i. Okay, multiplying complex numbers, yeah, you can do this the same as if they weren't, right? With the first, with this next example here, we're just going to multiply the complex number -5 minus I by 2, right? So we can just distribute that 2 times -5, of course, is -10, and 2 times -I is -2i. All right, what about here? Now here we're multiplying two complex numbers. The first one, the -3i, it does not have an imaginary, I'm sorry, it does not have a real component to it. It's just imaginary. So it's like it's one term being multiplied with two terms. So I can just distribute that -3i to both parts of the complex number. They're not actually terms, but I think you can think about them and deal with operations on them as if they were. All right, so -3i times -5 is going to be -15i, right? And the -3i times -I is going to be +3. But then look, we're multiplying I with I, so that's going to be +3i squared. Okay, +3i squared. Now, the way I've done that's not in its proper form, right, so far. I mean, I performed the multiplication, but now I need to simplify and write that complex number in its proper form. right? So I'm going to have to make a substitution for that I squared. If I by definition is the square root of -1, what does I squared have to be? If we square both sides, we can see that I squared is the square root of -1 squared, or -1, right? So whenever I see an I squared, I always want to make sure that I substitute that with -1, right? So when I make that substitution, then I'll have -15I plus 3 times -1. Well, of course, that's -15I minus 3. Now, is this done, though? Is that in proper form yet? No, it is not. The proper form for a complex number is A plus BI. The imaginary part has to come second. So my last step here is to put this in proper form and write it as -3 minus 15I. Okay, here's one very big difference between complex numbers and maybe a binomial, right? Complex numbers must be written in this form. They must be the real part first and the imaginary part second, right? You cannot have an I squared. If you've got one, substitute the -1 in, and you must rearrange it this way. All right, let's do one more multiplication. Here we're going to multiply two complex numbers, both with real components and imaginary components. All right. The method that we're going to do to multiply these is the same method we would use to multiply two binomials. Right? So we're going to multiply every term with every term. Even though they're not actually terms, we're thinking about this as terms. So we're going to multiply every part of the first complex number with every part of the second complex number. So first, we'll multiply 2 and -5, and that'll give us -10. Then we're going to multiply 2 and -I, and that'll give us -2I. All right, I'm going to have to multiply the -3I with a -5, so that'll give us a positive 15I. And then lastly, we want to multiply that -3I with the -I, and that will be positive 3I squared. All right, now we need to fix that, right? It's not in the right form. We're going to need to substitute -1 for that I squared, right? So then we would have -10, and then we can go ahead and combine these like terms here. -2I and positive 15I is going to be positive 13I, so I might do that right now. Okay, then plus that 3 times -1. So make that substitution there. All right. Now I like terms that I can combine, and with further simplification here, I can combine the -10 and the -3. So I'll have -13 plus 13I as my final answer. All right. So adding, subtracting, and multiplying complex numbers. Now we can also divide complex numbers, right? And dividing complex numbers is really just simplifying an expression with a complex number. Because recall, complex numbers must be in this form, A plus BI. Okay, we really don't want any denominators. I mean, A could be a fraction and B could be a fraction, but I definitely can't be in the denominator. Right? And fractions need to be reduced, so if they can be, they should be. So when I look at this first example here, 8 minus 3I divided by 4, I could rewrite that in its real and imaginary components, right? I could rewrite that as 8 over 4 minus 3I over 4, right? And 8 over 4, of course, is just 2. So this then would be 2 minus, and I can be up in that numerator, but generally B should be the coefficient to I, or should be in front of I, right? So I might say that's going to be 2 minus 3/4 I. Right? Look at the next example. Here we have I in the denominator. All right, so that's just got to change. We can't have that at all. Could I write them separately? I mean, I I could take that approach, but the easiest thing to do here is simply multiply by I over I, right? Because when I do that, when I multiply by, oops, I didn't mean I squared, I meant I over I. So when I multiply by I over I, that's 1, right? That's just 1. I'll end up with an I squared in the denominator, which I can substitute for -1. So I'll no longer have an I in my denominator, right? So let's do that multiplication. Let's see, in the numerator, I'm going to distribute that I. So I'll have 5I plus 2I squared. 5I plus 2I squared. And in the denominator, I'll have 3I squared. Okay, of course, I squared is -1. So this will become 5I plus 2 times -1 over 3 times -1. All right. Now the real part should come first and the imaginary part second. So I might just switch those. 2 times -1, of course, is -2, and then plus the 5I, he's positive, right, over -3, right? And then I can break it up and put it in its standard form. -2 divided by -3, of course, is 2/3. And then we've got a positive 5 over a -3, so that'd be a minus 5/3 I. All right. What about this guy, this last one? I need to get I out of the denominator. How do I do that? How do I get I out of the denominator? Well, the easiest thing to do is to multiply by the conjugate of the denominator, right? The conjugate of that denominator is going to be 1 plus 3I. So if I multiply both the numerator and the denominator by 1 plus 3I, I will no longer have an I in the denominator, right? Okay, so now I've got to multiply every term with every term because I have complex numbers with both real and imaginary components, right? So the numerator, I have a 6 times 1, that's a 6, plus a 6 times 3I, well, that's an 18I. Okay, then I got a I times 1, another 1I, and then lastly, an I times a 3I, that's going to be plus 3I squared. Okay, and down in the denominator, 1 times 1, of course, is 1. 1 times positive 3I is plus 3I. Then I have negative 3I times 1, so that's a minus 3I. And then negative 3I times positive 3I is going to be negative 9I squared. So do you see why multiplying by the conjugate over the conjugate eliminates I from the denominator? Look down there in the denominator. The I terms are going to add out, right? And this I squared is going to get substituted with a -1 as well as that one. Right, so further simplification gives us 6, 18I plus I, that's going to be plus 19I, and then 3 times -1 would be minus 3 over 1 plus 9 times, or minus 9 times -1, so that'd be plus 9. Right, combine like terms in the numerator. 6 minus 3 is 3. So we have 3 plus 19I over 1 plus 9, that's 10. And then I can break that up into 3/10 plus 19/10 I. Of course, and if I wanted to, I could write that as a decimal too. That's perfectly fine. I could also call this 0.3 plus 1.9I. Those are going to be exactly the same either way. All right. All right, so that was just a quick review of complex numbers. All right, what we really want to talk about here is the complex factorization theorem. All right, the complex factorization theorem builds on what we already know, about the relationship between the zeros of a function and the degree of the polynomial. right? The degree of the polynomial. So before, or last, let's see, I think it was in the last section, 3.5, we talked about that the number of real zeros of a polynomial has to be less than or equal to the degree of the polynomial. Remember that? Now, what we're going to do is add to that theorem. We're going to say that a polynomial has exactly n zeros, where n is the degree of the polynomial, right? That's the degree of the polynomial. So it has exactly the same number of zeros as the degree of the polynomial, but some of those might be complex, or all of them might be complex, right? As if you think about an upward-facing parabola that sits above the horizontal axis, right? That one has no real zeros, only complex. Right? So whatever the degree of that polynomial is, there will be that many zeros. They will be a combination, though, of real and or complex zeros. Okay, and then this is all worded nice and mathematical for you. Here's a nice mathematical definition. Let's take a look at an example of finding the zeros of a polynomial when not all of them are going to be real. All right. So when I go about finding the zeros of a polynomial, the first thing I do is I take a look at factoring. And this one is not going to factor nicely. So the next thing that I do then is I go ahead and I graph it. We all have graphing calculators, right? I go ahead and I graph that polynomial to look for where there might be a zero, okay? And sometimes I get lucky and it's a whole number, but not always, okay? But I just use that to help. Now, if I didn't have the graphing calculator, of course, I could find all of these zeros algebraically, right? I would start with Cauchy's bound, right? Cauchy's bound, which says that the interval that all the zeros are going to lie in, or lie between, right, is going to be plus or minus this constant, right, divided by the coefficient, all in absolute value, right? All in absolute value. So let's see, what do we call this? I forgot what we called it before, but maybe let me just call it m. I think we might have called it that. And then the leading coefficient, of course, is going to be a sub n. Maybe we'd call it that. Everything in absolute value. So Cauchy's bound tells us that the lower bound, limit or bound on the interval, which will contain all the zeros of the polynomial, is going to be negative 10 over 1 minus 1. And then the upper bound is going to be 10 over 1 plus 1, which of course is negative 11 to positive 11, right? So we know that the real zeros anyway are going to be in the interval between negative 11 and positive 11. That's a very nice starting point. And that can be very helpful in finding the correct viewing window on your graphing calculator as well. Okay, let's see if I could write that Cauchy's bound in the, be negative m over the absolute value of a sub n minus 1, and then positive m over the absolute value of a sub n plus 1. There. That's the formula there for Cauchy's bound. So that tells us our interval. Now, what can those real zeros possibly be? Well, that's our plus or minus p over q situation, right? Plus or minus p over q, where I've got to find all the factors of the constant term and all the factors of the leading term, right? So all the possible zeros are going to be plus or minus p over q, all right? P is going to be factors of the constant term, and q is going to be factors of the of a sub n, right? So let's write them out. Since a sub n is just 1, I don't have to worry about any fractions, plus or minus p over q is just going to be all the factors of m. So it's going to be plus or minus 1, plus or minus 2, plus or minus 5, and then plus or minus 10. Right? So that gave me several possible real zeros. Right? I know all the real zeros are between negative 11 and 11. Here's all the possible real zeros. Okay, now is a good opportunity to look at my graph on my calculator to see to find at least one of them. Okay, so when I look at my calculator, I can see that there's a real zero. There's a real zero at x equals 2. Oops, that's an equal. At x equals 2. You know, from the calculator, from the graph. Okay. So to find the rest of them, I'm going to have to do long division. Right? This real 0 of 2 would come from the factor x minus 2, right? So I'm going to now divide, I'm going to have to divide my polynomial by x minus 2, all right? So let's do long division. We're going to divide x minus 2 into x cubed minus 4x squared plus 9x minus 10, right? And this is going to give me the remaining polynomial, or the factor with x minus 2, all right? All right, so x goes into x cubed, x squared times, so put that in our x squared column, put x squared over there in our x squared column, x squared times x, of course, is x cubed, x squared times negative 2 is negative 2x squared. Negative 4x squared minus a negative 2x squared, well, that's negative 4 plus 2, so that's going to be a negative 2x squared. All right, let's bring down the 9x. It's positive, so bring down that plus 9x. All right, x goes into negative 2x squared, negative 2x times. So we'll put that negative 2x up there. We'll multiply it back out. Negative 2x times negative 2 is positive 4x, right? Now we'll subtract that out. And we're left with 5x. And we'll bring down that negative 10. And x goes into 5x 5 times, positive 5 times. When we multiply that out and subtract it, as expected, we see that there is a remainder of 0, right? Remainder of 0. So now we have f of x in a partially factored form, right? It's x minus 2 times x squared minus 2x plus 5. All right, and so we have to find the remaining zeros. We're going to have to continue to factor or solve x squared minus 2x plus 5, that remaining factor, right? I can see that that isn't going to factor any further. So then to find the remaining zeros, I'm going to have to set that trinomial equal to 0 and solve. Since that happens to be quadratic, right? I know that I can use the quadratic formula on it, right? The quadratic formula tells us that x is negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is the coefficient of the x squared term, b is the coefficient of the x term, and c is the coefficient. I didn't mean an x there. And c is the constant term. C is the constant term. All right, so let's find out what that is. Negative b would be negative of negative 2 plus or minus the square root of, now b squared, that's going to be negative 2 squared, minus 4 times a, which is just 1, times c, my constant term is 5, all over 2a, well, that's 2 times 1. Okay, so when I simplify that, I get 2 plus or minus the square root of let's see, 4 minus 20, right? Or negative 16 all over 2. Okay, so I've got a non-real, oops, I didn't mean that, let's put that back. I've got a non-real portion. I've got a negative radicand under an even root, so I'm going to need to introduce I, right? So then I can rewrite this as 2 plus or minus I square roots of 16 over 2, which of course is 2 plus or minus square root of 16 is 4, right? So 4I over 2. All right, so if I write that separately, there's going to be 2 separate ones here, right? Let's go up here and finish. I'll have 2 over 2 plus, well, let's do the minus first, minus 4I over 2. And then I'll have 2 over 2 plus 4I over 2. Of course, these reduce, right? 2 over 2 is just 1. 4I divided by 2 is 2I. So we have 1 minus 2I as one answer. And then we have 1 plus 2I as a second answer. Right? So what are all the zeros here? The zeros of f of x are 1 minus 2I, 1 plus 2I, and then what was that real zero? We can't forget him, 2. There are 3 zeros. What is the degree in the polynomial? 3. So of course there's exactly 3 zeros. Okay, that ends the lecture.